Alright, so as you've seen, the question today has to do with mirrors that you find in stores. You'll often see a mirror hanging in the corner of a store, and it's curved. Why do you see that mirror there, you think? Yes?
Because the mirror finds different corners that you can't see when you're just looking straight on, so they can see if someone's shoplifting or robbing you.
Yeah, exactly. All sorts of reasons. When you have a curved mirror like that, you can see around halls, see around the aisles there, so maybe that way you don't run into somebody that's coming the other way because you can see each other. Shoplifting is definitely one. So yeah, any of those ideas are just fine. There's all sorts of reasons you'd like to be able to see a little bit more of the store from one location. Very nice. Good ideas. Now, of course, we're going to be dealing with curved mirrors today then. And that's the main purpose of what we're going to be talking about. So in order to figure some things out about curved mirrors, I'm going to pass them out to you. And we're going to see if we can draw a few deductions based on what you see here. I'll see if I can do, I don't know if I got enough for one per table.
These are heavy. Oh. Oh, wait, is it the other way? I see you, bro.
Those are two different kinds.
I see Sam too.
Two different kinds there.
Oh, it's the other
And
way.
these are two different kinds. I'm going to go ahead and, Lexa, I'm going to take yours. Why don't you share with Brooke? That way the folks in the back can have one too. So,
I'm upside down.
we're going to be dealing with curved mirrors today, and the main thing, again, in physics is we have to explain what it is that we observe. It's not just about observing things and noticing things that seem interesting. We actually have to explain why we see them that way. And so far in this chapter, it's been about explaining those things using light rays. And that's exactly what we're going to be continuing with today. There are two different kinds of mirrors that you have with you. They are concave and convex. And you'll be taking notes today, so feel free to get those out.
It's already September.
I know, right? September is a good month. I'm actually going to use brand new whiteboard markers for this, because this is a pretty important day of notes. Right? So concave mirrors are kind of like this. The shiny side, the reflecting side, is on the left. Convex is the exact opposite. So for the concave, the shiny reflective side is the one that's curving in. Convex, it's the opposite. If you continue to convex mirror all the way around, you'd have a big ball.
So the lines on the back side of the mirror?
The lines represent the side that is not reflecting. Yep. Another way to describe concave mirrors are converging mirrors. This will probably be the easier way to remember these. Of course, this is diverging then. And you'll see why we call them these things shortly. So, once again, we got to explain what we see with these mirrors. We see different things based on the sides that we're looking at and the distance we hold those mirrors away from our face. So first, we kind of want to think about what's going on with the light rays when they impact these mirrors here. In order to figure this out, I have no idea how well this is going to show up on the on the camera that's recording this, but we'll see and give it our best try. By we, I just mean me. I'm going to go ahead and borrow that one real quick. Thank you. So these here are a bunch of lasers. Yeah, there they are. Try and get them all about the same area there. And so one of the ways we can figure out what happens with light rays when they impact these mirrors is just by sticking them in front of the laser beam and seeing what happens. Now, we wouldn't be able to see this too well if we were just doing it with the red lasers. The reason for that is because, that's kind of cool. The reason for that is because there's not too many particles in the air. So what we have to do is add some particles in the air so that these laser beams have something to reflect off of, which is why the physics fog machine is making its first appearance in this class. So let's see what happens. First, we're going to look at the mirror that, when you look at it, it's curved inwards, the reflective side. So we're going to look at the concave mirror first, convex second, and see what happens. So there are our laser beams. And I'll try and stick this in there before it all dissipates.
Whoa.
So, if I hold it like this, it's kind of harder to see, but if I angle it up, you can see a little bit clearer what's happening here. What's going on with the light rays? Are they coming together or are they spreading out? Yeah, eventually they spread out, but they're coming together first. That's what's happening if you're looking at it here, right here. If you're looking at it up here, they're coming together about this location, and then they spread out afterwards. I wonder if I can see if I can make the camera see any of this. Alright, camera people. I'm going to see if I can show this to you. So the light rays, well, it looks cool. I don't think they can actually tell what's happening, though. But yeah, the light rays are coming together in one location. This type of mirror takes these light rays and it brings them together. After they come together, they do spread out. Now the other kind of mirror is the one that takes the light rays and diverges them apart. And I'll just show that example next. Here it's pretty clearly these light rays are hitting it and spreading out immediately. They're not coming together first. And it doesn't matter where I put this, it's just going to take those light rays and spread them out. So that's why this is called a diverging mirror. And this is kind of the first way, and the fog machine's taking a break. If we got time, we'll do that again at the end. Yeah, don't breathe it in too heavily. That's asbestos smoke. Official fog of Mr. Hathaway's classroom. Okay. Okay, there we go. So we got to explain what we saw, and we have to explain how it makes images appear on these mirrors. So, take a look at the mirror that has the side that's shiny going inwards, the concave side of your mirror. Yeah. So, take a look at that. Hold it far away from your face. And look at yourself.
I'm upside down.
You're upside down. Absolutely. Would you say that you appear bigger or smaller than normal when you do that? A little bit bigger, perhaps? The main thing that you'll notice is that you are upside down. So we have to figure out why it is that you appear upside down in this kind of a mirror. So here's where your notes are going to start. So we've got a mirror that looks kind of like this. It's curved inward. It is a converging mirror. The light rays are going to come in and then converge together to a point. And I want you to go ahead and label one spot on it F, and then label one spot on it C. And somewhere around the C, we're going to put an object. We're going to represent that object just with an arrow. So again, what we notice is that we're upside down, and hopefully we can somehow explain that using light rays. And that's what we're going to do. Now, one thing else that you need to write down in your notes before we continue with this is this information. You don't know what it means right now, but you will come to see this as invaluable shortly. So when you're trying to figure out where this image from this object shows up and its characteristics, you need to do so with light rays. And whenever we do that, generally we want to take those light rays and begin them at the top of the object. In addition to that, the first light ray that you draw coming off of this object ought to be parallel to this dotted line. So, I'm going to draw a light ray that goes parallel, and this is the first step to each and every problem that you see for this type of a scenario. So again, this red arrow is the object. This is our first light ray here. So that light ray is coming off of the object going parallel. Any parallel light ray coming off this object is going to go through the focal point. Which spot do you suppose is the focal point? What's it? The F, absolutely. This F stands for focal point. All parallel light rays hitting this mirror will travel through this location. So that's the first thing you have to do. That's the first light ray you're going to draw. It comes out parallel, hits the mirror, goes through the focal point. The next light ray is going to go through the focal point. So I'm going to start from the exact same position, the tip of the arrow. Light ray goes through the focal point. And what do you suppose happens to this light ray after it goes through and hits the mirror? It bounces, and it bounces out Parallel, absolutely. And that's what this relationship means. If you begin with a parallel light ray and it hits the mirror, then it's going to bounce off and go through the focal point. If you have a light ray going through the focal point, it's going to hit the mirror and come out parallel. And that's what we have happening right here. And that's as far as you need to go. If you would take these two light rays that have hit the mirror, you'll notice they cross right here. Now again, these light rays are coming from the tip of the arrow. So what this means is that where these light rays cross here, this is where your image is going to form. This is where the image of the tip of that arrow is going to be located. So you can just draw your image right there. So when you have an object positioned here for this type of a mirror, and you draw the light rays, they come together right there, and your brain interprets the object as looking like this at this location. Is this upside down or right side up? It's upside down, just like you were when you held that mirror far away from your face. This is why you see things that way, explained through light rays. Now the last thing on this thing says center of curvature and right back. What that means is that if this object was a little bit further back and I could send a light ray through the center of curvature and have it hit the mirror, it would bounce and go straight back where it came from. The reason I don't do that typically, as opposed to these two light rays, is because sometimes, like in this case, you're not going to have it hit the actual mirror that you drew because it's too close to the center of curvature. But if that's something you want to use under certain conditions to see if your image position is correct, then feel free to do that. But yeah, because these are actual real light rays that are coming together here, this is going to be a real image. And for the record, it's inverted, of course. And that's how that works. Questions on any part of this? Now, there are really three different scenarios you're going to see with curved mirrors. This is the first, and it's the easiest. So we got to take care of the other two now. The mirror that's in front of you, the same side that you looked at and found that you were upside down, take that same mirror, bring it really close to your face, and tell me what you see. You see yourself, of course. Are you upside down or right side up? You're right side up. Are you bigger than normal or smaller? Bigger. Okay. So we have to use this same setup, this same idea, to explain why it is that when you hold this far away, you look upside down, but when you bring it close to your face, you look bigger and upright. And hopefully it works. We'll find out. So I'm going to use this same mirror here. You're going to want to draw a separate one in your notes. We're going to change the location of the object for this. No longer is it a ways back from the mirror, like when you held that far away from your face. Now our object is going to be much closer. And we'll see what kind of answer we get this time. Yeah. Here's the pass and stuff. I have my signature on it. Just fill it out as far as you need. So now our object is in between the focal point and the actual mirror. And just for the sake of, so that you know what these two things really represent, the focal point is the spot where any parallel light ray hitting this mirror, all of those light rays would pass through that location. There's a parallel light ray coming in here, it would go through it. Up here, it would go through it. And the center of curvature represents the very middle of the mirror if you continued it forever. If this mirror continued forever in a big circle and you ended up with a Christmas ornament, the center of curvature would be at the very middle of that. Be at the very center of that ornament. Okay, so what do you suppose we should do first? What kind of light ray? Parallel! So that light ray goes in, nice and parallel, just like the first time. And where do you suppose that light ray bounces and passes through? You got it. There she goes. And now we got to do the focal point parallel light ray, so I'm going to draw a light ray that goes through the... Oh, no. Well, we can't draw a light ray through the focal point now because we're in front of the focal point. If I shot it back this way, it's not going to hit the mirror. So when you have an object that's in front of the focal point, this rule still applies. It's going to have something to do with the focal point, and it's going to somehow pop out parallel. But instead of going through the focal point first, what you do in this scenario is you line up that tip of your object with the focal point. I'll just do a dotted line so you can see that's what it's lined up with. And then it seems to come from that location. It's lined up with the focal point. And if that's the case, it will, yes, hit the mirror and come out parallel. Huh. Well, now this poses an interesting conundrum here, doesn't it? Where's my image going to form? Who knows, right? Because these light rays aren't crossing like they did the last time. And so here's the thing. When you've got two light rays and they don't cross, if they're moving away from each other, what you do to find your image location is you take these two reflected light rays and you follow them backwards behind the mirror until they cross. They cross at this location right here, so that means that's where the tip of this arrow is going to form. So I could draw my image like this. Well, now that explains the observations, doesn't it? When we looked at that mirror and we held it close to our face looked bigger and it looked upright. And that's exactly what we get with this image. A bigger image than the actual object, and it's upright. So you could say it's bigger than the image. You could say it's upright. And would you say that this is real or virtual? Any guesses?
Virtual.
Why would you say virtual? That's actually exactly correct. So here's the thing. If you're on the other side of the mirror, no actual light rays are going to come over here. No real light rays are going to make it this far. Only pretend light rays will, or virtual light rays. Because this object forms due to a reunion of virtual light rays, or pretend light rays, it is a virtual image. A neat little way that you can kind of remember this, if you're not quite sure on a certain one, virtual images are almost always upright, and real images are almost always upside down. Alrighty. Well, we've got one more scenario that we need to talk about. That's with the second mirror that's in front of you. So that's the one that's going to be the diverging mirror. The shiny side is the rounded outside side of it. And I'd like you to take that mirror, hold it far away from your face, bring it in close, see if anything changes when you do that.
It goes up that way.
What's that?
The one that can, like that caves in, right?
No, the other one.
Well,
So when you bring it close and put it far away, do you stay upside down or upright, or are you flipping like the other side? What's going on? You stay the same. You stay upright the entire time. In general, when you're observing your pretty face, would you say that you are bigger or smaller than normal in the image? Yeah, you appear smaller than normal. If you hold this away from yourself and you're looking, I know for me, I look like mini Mr. Hathaway right now. I look much smaller than if I was using a normal mirror. So somehow we have to explain that using light ray diagrams and this new mirror. So let's see what we can do here. And this will be our last setup for this. So now the mirror looks like that. The shiny side is on the left. Put the focal point right about there. Center of curvature is over there too. And we'll do the object right here.
How could the focal point and the center be on that center?
Well, because this is a diverging mirror, any parallel light rays that hit it are just going to spread out. So they're not going to come together at a focal point on this side. So same thing with the center of curvature. These two things are going to be on the right because it's curving that way. These two values will always be located on the side that's curving with it.
So whenever it's diverging, the focal point is on the other side?
Yeah. And these will typically be listed for you. You don't need to use these on this side of the mirror. You'll just be using them on that side, as you'll see. So, what kind of light ray should we throw into it first? You got it. Parallel light ray coming at you. Hits the mirror. Now, once again, this light ray is not going to bounce off the mirror and go through the focal point, because there's no focal point over here. And even if there was, this is a diverging mirror. It's going to take this light ray and it's going to shoot it off upwards, because that's just what diverging mirrors do. It spreads them out. So, this still has to be true, though. There still is that relationship between a parallel light ray and the focal point. So, if you can kind of imagine, this light ray is going to hit that mirror. It's going to bounce up like this. You got it. Right on the money. We line up the spot where it hits the mirror with the focal point. Just do a little dotted line to show that. It's going to hit the mirror and bounce up at that angle, as though it had come from the focal point. Now for the next light ray, focal point parallel, there is no focal point over here. And even if there was, if I shot a light ray through it, it would hit the mirror and spread it out even more. It would not go parallel from the focal point. So what we do in that case, focal point parallel, is we aim the light ray at the focal point behind the mirror. It's going to hit the mirror there. And I'll, if you want to draw a dotted line from there to the focal point, that's fine. I'll just leave it like this for now. But because it's aimed at the focal point, it's going to hit that mirror and it's going to come out parallel. And once again, we have a situation where these two light rays are never going to cross. And that's sad, because they started in the same location and they're never ever going to see each other again. But for these conditions, we take the two light rays, we follow them back behind the mirror like we did last time until they cross. So in this case, they cross right about there. So that's where the tip of your arrow or object will form, and you have your image. So it's upright, it's smaller, and would you say virtual or real? Yep. For two reasons. Number one, it's upright, so it's almost always going to be virtual. And the second reason is that it's a reunion of these pretend light rays, these virtual light rays. Very good. And that's exactly what we see when we look at a mirror like this. Whether we hold it far away or close to our face, then we always see an image that's upright, smaller, and virtual. And that's how that works. Questions on any of this? Another little tidbit. Your focal point is always directly between the center of curvature and the actual mirror, if that would help you out at some point. All right, because chapel ran a little bit long, you're not going to have time in class to work on this, but I'll hand it out, and I'll do my best to get through, like, question number 1 with you.
Put it back in the drawer.
What's that?
I said put it back in the drawer.
Oh, put it back in the drawer.
Yeah.
Yeah.
And this is going to be, this will be due tomorrow. Most, well, just like the other homework, you're just drawing lines. So there are a fair amount to draw, but they're just like what we did in class. So do the very best you can. Use a straight edge. Make sure to put arrows on your rays. And again, remember, this all just needs to be attempted by the time you get back to class tomorrow. Everything needs to be attempted. Whether it's right or wrong, we'll figure that out tomorrow when we go through it. Everything on this should look exactly like what we did up here, except number 1 and 2. So I'm going to see if I can get through number 1 with you, and then you should be good as gold. So number 1 says, draw in at least 2 incident rays from the tip of the object along with their reflected rays. Use your light rays to figure out where the image is and draw it. Trace the path of the given ray after it reflects off of the mirror. Okay, so basically here's what this is saying. All right, 1 minute. All right. Watch and hold on for dear life. So one of the main things is you got to figure out where this ray goes. And in order to figure out where it goes, you got to know where the image forms. So I'm going to have to pass on the straight edge for this to do it in time. So you just got to do what we did in class for this type of mirror. Parallel light ray comes in. It hits the mirror. It goes through the focal point. Another light ray will go through the focal point, hit the mirror, and come out parallel. That means your arrow tip is formed right here. You don't have to draw the rest of the object. If you really want to be specific, you can continue it up. So that's where the image is formed. So then all you do is you got to find out where this ray is going to go. Where do you suppose it's going to go? Yeah, right through the intersection. Because all the light rays coming from the tip of that arrow are going to pass through this point, because that's where the tip of the arrow forms. And you do the same thing for number 2. And like I said, everything else was stuff we pretty much did directly on the whiteboard here in class. So don't overthink page 1. That's the idea. You guys have a good day.